Good morning. My name is Richard Reister, and I'm the Program Manager for the Light Water Reactor Sustainability Program at the Department of Energy, and I'll be covering the next topic, which is RC5, and it's titled Economic Valuation Techniques for Integration with Safety Margin Characterization. First, I'll provide an overview of the Light Water Reactor Sustainability Program, and then I'll go into a little bit more detail on risk-informed safety margin characterization pathway, and then talk about the specific call. The Light Water Reactor Sustainability Program seeks to enable the existing nuclear power plants to operate for an extended period of time, generally beyond 60 years. And so there's the goals are to develop the fundamental scientific basis to understand, predict, and measure the changes in materials as they age, to apply this knowledge to develop methods and technologies to support the safe and economical long-term operation, and research new technologies that enhance plant performance, economics, and safety. Again, all focused on keeping the existing plants operating. We coordinate this program with industry, primarily through the Electric Power Research Institute, but also other organizations in industry. And we also coordinate this program closely with the Nuclear Regulatory Commission. And we also use cost share in this program with industry to leverage resources. We divide the program up into four what we call technology pathways. I'll describe them briefly and then get into more detail on the risk-informed safety margin characterization pathway. The first is material aging and degradation. It's the biggest pathway, and it's focused on understanding the materials as they age in long-term environments in reactors, so high temperatures, high radiation. So we provide data on the performance in support of licensing. We also focus on means to detect and characterize the aging degradation process. In the risk-informed safety margin characterization pathway, we're developing tools for industry to allow them to better understand the impacts of replacement and repair decisions on safety and reliability that will ultimately influence decisions related to long-term operation. And I'll cover that in more detail later. The third pathway is the Advanced Instrumentation Information and Control System technologies, and we look at the aging of I&C technologies and the upgrade of these technologies in existing plants, mostly focused on improving the economics and long-term viability of the plants. And finally, in our fourth pathway, it's a catch-all for emerging issues. And right now we're focused on two issues. One is the backfit of cooling towers to address some environmental concerns, and the lessons learned impacts from the Fukushima accident. So focusing on the risk-informed safety margin characterization pathway, subject to this call, the focus is develop techniques to conduct margins analysis. This includes methodology for carrying out simulation-based studies of margins, safety margins. So a big part of the focus of this pathway is the development of these tools. The biggest tool that we're working on is Relapse 7, and this is a systems code that simulates behavior at the plant level, and it would allow it's a computational tool that would allow faster and more accurate analysis. There's RAVEN, the Risk Analysis Virtual Environment is the acronym, but it's a simulation controller, and it's what drives the simulation scenarios. So it's the heads, or the controlling element. So it drives the scenario of the simulation that you're interested in. And finally, there's GRIZZLY, which is a component aging and damage evolution model. And we'll couple that with Raven and RELAP 7. So a quick overview of the RISMAC pathway. The purpose is to support plant decisions for risk-informed margins management in support of improved economics, highlighted for this call, reliability and sustained safety. So the goals are develop and demonstrate a risk assessment methodology coupled to safety margin quantification that can be used by plant decision makers. So it's important that this is a decision-making tool primarily and not a regulatory tool. And to do this, we're creating an advanced RISMAC toolkit, and that would enable more accurate representation of plant safety margin. And again, the key capability is to allow for better safety margin management as plants age, and as other changes are made to the plant. Examples might be power uprates or other plant modifications. So you're managing the safety margin of the plant as these changes occur. The next slide is just kind of a graphic related to that, the toolkit, but I would emphasize the lower part, which is these are all built on the MOOS framework, which is the multi-physics object-oriented simulation environment, is the toolkit that all these applications are written on. So it's the unifying element and the enabling technology. So just briefly on the safety margins calculations. So the loads and the capacities are uncertain and can be treated probabilistically. So the example here shows the, if you run a scenario and you treat probabilistically what will happen during that scenario, you'll get a number of outcomes that can be then plotted on a graph. And this is just an example of one way to show an output from this type of analysis. But you can see that each scenario ends up with in this case, a peak cladding temperature as a measure of performance. So you can see you get a distribution based on running the same scenario but different probabilities of events occurring. And then you could study, for example, two alternatives to see how the different outcomes, your safety margin, which is the comparison of, in this case, it's really a point comparison to a parameter or criteria, the 2200 degrees limit of cladding. But actually, that limit could be also a probability distribution. But in this case, we use a point limit and just use that as a comparison. So this is just an example of what type of output you'd get from the analysis. But one thing that we don't have right now for each of these scenarios that are run is any type of economic impacts. So for each scenario, various things might happen. You might get a plant outage. You might have damage to equipment. You might, in the case of when you get into accident space, you might have a severe accident. You might get either some minor fuel failures or major fuel failures. All these have potential economic impacts. And so the whole point of the call is to try to incorporate these economic impacts into the model so that the decision makers will be able to factor in economics into their decision making. So the challenge is concerning economics, and so the current limitation exists representing probabilistic costs. So just as we treat the plant probabilistically, we'd want to treat the economic impacts in a probabilistic way. So we're not just concerned with accident costs, but also less severe impacts, like I mentioned, damage to equipment, outage time, all have economic impacts. So we want to look at how the RISMAC toolkit, we can add the modeling of economic issues into the RISMAC toolkit. And this includes the uncertainties that could be present when considering these economic impacts. And also how to validate these, just like we validate the information, the probabilities of the plant response, we want to be able to validate the probabilities of the economic response. So again, the topic is the economic validation techniques for integration into the safety margin characterization process. So the goal is to provide a way to determine economic implications related to safety, plant degradations, outages, accidents, worker impacts, another example, such that additional information can be incorporated into a plant decision-making process. So as I mentioned, the gap in modeling for nuclear facilities is the modeling of economic impacts. So the toolkit we're developing is used to predict the consequences associated with a scenario from different alternatives. However, the economics are not currently considered, and that's what we're adding. So we're asking for researchers to provide models and tools that can be integrated into the RISMAC toolkit. And when we say integrated into the toolkit, a major part of that is making it compatible with the existing toolkit, which is all, again, based on the Moose platform. I'd note that what traditionally in this area there are methods used for asset management and plant life cycle. Cost considerations, these are not desired as part of this work scope. So I just want to make that distinction. And I think I've already covered most of this, but it's restating the work scope description that to provide the economic model into the RISMAC framework. So I think that's all I have. The technical point of contact for this work scope is Curtis Smith at Idaho National Laboratory, and I think we're going to try to have him be online as well, so he can address any of the more technical questions if we have any. So,
Curtis, are you there?
Yes.
I heard.
Okay, our first question is, can other codes be used, e.g. RELAP 5 with best estimate and uncertainty techniques that incorporate economics?
I think the short answer is yes. For example, right now we have ways to call RELAP 5 within the toolkit that we've developed, and so I guess the part of the research would be how to extract the economic information from if you had that kind of a coupling. But yes, I think is the answer.
How can I obtain documentation giving details of the Moose framework?
Yeah, we have a couple of things. We have, for example, Moose training material, and you can send an email to me. My INL email address is curtis.smith@inl.gov, and then we can get you information related to the Moose platform and some of the tools we've actually built on that platform.